properly. All right, and our final talk of this session is Sam Ragland, who will be talking about the satellite guide star adaptive optics for LBT.
It's a pleasure to be with you this morning. I'm Sam Ragland. I am the head of the adaptive optics group at the Large Binocular Telescope. I'll be talking about a new instrument concept that we are proposing to develop at LBT. Here's the proposing team. It involves folks from NASA, MIT, Optical Sciences, Steward Observatory, besides LBT. In addition, there are over 40 individuals from over a dozen institutions are involved in this project. I couldn't list them all here. And I'm open to new collaborations. Please reach out to me if you're interested in this project. LBT is the first of emerging generation of extremely large telescopes. It has two 8.4 meter aperture with an edge-to-edge baseline of close to 23 meters. And we propose developing a next generation adaptive optics system on the telescope. We anticipate rapid development without impacting science operation as we propose to implement it in an currently unused bent Gregorian focus on the system that's shown on the bottom right image with a box. Okay. That is the focus. It's called Link Nirvana. It has two left and right, and we'll be using one of the proposing to use one of the both. Okay. Yeah, our focus is on improving the detection and image contrast in the context of exoplanet science, as well as protoplanetary disk detection and characterization. And what's shown here is contrast. It's taken from Follett in 2023, shows all the current contrast of existing instruments in solid lines, and the proposed future ones with dotted. Okay. And LBT does have high contrast instruments, but they are currently exhibiting a wide range of detection limits. Yeah, what's shown is the 5 sigma contrast post-processed detection limits. Okay. So it falls in we are more focused towards close to the star, which we are talking about a few lambda or D region. That's why I shown that region. It has a pretty wide detection limit depending on the condition of the during the observation, basically the seeing condition. So we propose developing what we call agile extreme adaptive optics to address varying atmospheric seeing conditions to have a more stable and high performing system. And by doing this, we anticipate enhancing the detection limit by about 2 magnitude for very bright stars under typical moderate seeing at the Mount Graham site, as well as enabling observing fainter targets. Okay. So it's a synergy with Orcus mission. Orcus mission is a novel space-ground hybrid observing concept that utilizes uses bright artificial guide stars from space and observe with ground-based telescope that are equipped with high-performance adaptive optics system. Okay. So this is the planned orbit of Orcus. It's in a highly elliptical orbit with what's shown on the top right. The green spots are the regions. At least you will have 3 observing opportunities. If the satellite is proposed to be launched with a 5-day period, so you'll have at least 3 observing opportunity when the satellite is pretty far from Earth, about 200,000 kilometers. Okay. So the guide star will act pretty much like a natural guide star. It's pretty bright, can be from 0th to 5th magnitude lasers. And our project, what we call Sagi-star, would enable LBT to be potentially one of the ground stations for the workers project. And this would enable reaching very faint targets, which is otherwise not observable. So what's shown here is the expected performance. All the simulations were made with assuming workers to work with Keck, that is Keck telescope. That is one of the planned the ground station. So we are proposing to use LBTs as well. So on the left, what's shown is the angular resolution, and the bottom left, you can see you could reach around 20 millisecond angular resolution. It's already been reached both at Keck and LBT, but on bright targets observed with the short exposure and by shift and adding, we can reach. But the goal is you have to be able to take very long exposures, like typically an hour or so, to reach the kind of sensitivity limits required. That's shown on the right. So we propose developing technologies that would enable us to do that. So here are the key science from worker science, ranges from cosmology to our own solar system. And here are the projected performance. Just one test case. These are simulated images for a galaxy merger, NGC 2623, assuming the binaries are separated by 5 parsec. This is the projected performance for typically a 8 to 10 meter class telescope with workers. Okay. And as you can see in the bottom right image, it's a little hard to see. You can detect a binary agents from such a advanced system, combined space ground system. So here's the Sagi-star instrumentation. It aims to implement advanced capability, not only for hybrid space ground observing, but also to enhance the standard ground-based EVOP observations that's currently in place at LBT and other 8 to 10 meter class telescopes. Okay. So it involves various subsystems. I don't have time to go into all the details, but I'll try to quickly give a feel for some of the major systems and where we stand. Okay. So the very first one needed is a variable fine off-axis guiding. Because currently we use a natural guide star. Often the guide star itself is the science target, but on the other hand, the satellite will be drifting across the field. In about 2.5 hours, it will be passing through the science target of your interest within about 7 or second field of view. So we propose developing a fine guide star facility. What's shown on the bottom right is schematics of the one of the focal plane station at the LBT. Currently, it's populated with a lot of hardware. That's what you see. But we propose replacing this with mostly existing spares with a few hardware. We propose developing a system that would enable us to not only add a new capability, because we'll be able to reach fainter target, but also demonstrate hybrid observing using existing communication satellites. So we plan to also install an instrument called ROSI. It's already funded through a different program in Italy, and also plan to install a fiber injection unit to enable EVO corrected mode on a workhorse high spectral resolution instrument called Pepsi that's operational at LBT. As I mentioned, it will facilitate early EVO science on faint target, as well as demonstrating the concept. This would help, we believe it will help us to get secure funding for future developments. Okay. So there are the other major systems are near-infrared wavefront sensor that we plan to install again on the same bench above or below. And this would enable even fainter targets, especially the highly redundant objects in the visible object, like protoplanetary disks and protoplanets, like that. The near-infrared wavefront sensor, we plan to design it to accept both beams. Although we currently have access to only one side, there's another instrument is being developed that would take over the SX that is on the left of the figure. But we plan to design a system that would accept two input, that would open up the possibility of facing the telescope aperture of both telescopes. The future that would enable piezo imaging. And the another unit is a high density deformable mirror. We are looking into implementing a 3K deformable mirror. And in addition, developing a flexible real-time control system that is crucial to implement some advanced wavefront sensing, like control algorithm, like spectral annealing, predictive wavefront control, machine learning, things like that. That's currently not possible at the AO systems. So here's the rough timeline. So we are focusing on phase 1 through existing internal funding as well between LBT and other partners, co-PIs, that would enable new NGS science as well as demo for satellite hybrid configuration. But the phase 2 and phase 3 will require external funding. That's what we are looking into now, writing proposals, and we hope to submit funding proposals this year for the development of phase 2 and 3. And the phase 4 that will start a little later, that would enable that aims at implementing similar capability on the other side of the aperture, so that ultimately we could do piezo imaging. That's basically an optical interferometry. I'll stop here and take questions.
Okay, how much do you decide when the Sagi-star going to be moving relative to your target star, like from it or something?
Yeah, it's about over the field of 14 arc seconds, will take about 2.5 hours. But on the other hand, if the target is of high value, you should be able to remaneuver the satellite to, get the object on axis. But typically for the power, the ORCAS is planning, you don't plan to do frequent that kind of maneuver. Okay. So that's the 2.5 hours of observing.
Thanks. I just want clarification is if you're talking about hybrid guiding, are you having the wavefront sensor follow the satellite differently from the science?
Yeah, that's exactly. So that's the plan. That's what we plan to do in the near future, in a year, to demonstrate on the LBT. Thank you.
How far off axis can you guide with this new wavefront system?
Yeah, it will be, we are targeting 40 arc seconds. So all 40. Yeah. So that is the optical design. It looks like it's easy to go. If you want to go larger, you require a little complex optics. So not only for the satellite, we want to use it for ground-based observations as well. So that's the goal. Okay. Thank you.